Hi, my name is Mahdi J, and I'm from University of Windsor, Canada. In this presentation, I present one of our research work in a smart grid, time series load data analysis for user power profiling. In this work, I have two colleagues, Min Chang Kim from E3, South Korea, and Dima Al-Hadidi from University of Windsor, Canada, which helped me to conduct this research. This presentation, first, I review a smart grid and big data of users' power consumption, dynamic time warping clustering algorithm will be reviewed in the next. I introduce power profiling of smart grid customers, and also how we can analyze and how we suggest to analyze users' time series load data. The analysis and conclusion are the last part of this presentation. Okay, a smart grid. A smart grid is a complex system of systems. And by default, a smart grid has 7 different parts, namely operation, power transmission, distribution, and customer. And also we have 3 more entities: service providers, operators, and also marketing. But basically, we consider 4 main part of a smart grid as operation, power, operation, transmission, distribution, and consumer. Normally, in customer side, to monitor users' power consumption and measure the level of load data, normally we use special infrastructure called advanced metering infrastructure, AMI. AMI is a network of smart devices or smart meters, and those meters collect users' power usage automatically during the measurement period. And in this case, normally AMI make us access to users to each individual place, at user's place, and to have real-time consumption data, and those data automatically is uploaded to our smart grid. So we have a huge amount of data, huge amount of load data of users, which is reported automatically to our network. Moreover, that one, normally AMI provide a dual direction connection between a smart grid and user to a smart grid. So not only users' data consumption is reported to a smart grid, but also command and any special information from a smart grid can be delivered to users' place, like demand response system. This is the property of or the benefit of AMI. So in the view of data automatically generated and reported to a smart grid, we can see that a huge amount of data of users' consumption is reported to a smart grid. And this data is very valuable for different purpose and application for a smart grid management. So normally users power consumption data is analyzed and used for different purposes like expansion, path planning, load forecasting, performance analyzing, abnormality detection, or demand management. So this data, which is very helpful for network management and smart grid management, is available automatically to the network. Moreover, those management purposes, we by analyzing users' consumption data, we are able to profile and find users' power consumption behavior. So based on that behavior, you are able to predict what what would be the next amount of usage or of the users in the next period of measurement and etc. So based on this on data analyzing, we have special concepts available for our smart grid power management, power profiling. While users consumption behavior is different and they consume differently, but normally typically users exhibit a certain amount of repetition. So by analyzing users' behavior for a long time, for a long duration, we can detect that pattern, fixed pattern of users' consumption and power consumption. So by power profiling, we extract users' power usage pattern for a given period. And by this case, we are able to have some handy tool for a smart grid management, like demand response management or load forecasting. Normally, a user's profile is affected by different factors like the load pattern of the devices which users use, the user's consumption behavior, contextual factor like time, location, environment, and etc. But basically, two main tools and solutions which use for power profiling are pattern extraction and classification. So, yeah, this is for power profiling. For classification, as I mentioned, in our suggested model, we use DTW or dynamic time warping clustering algorithm. Actually, DTW is a very popular tool in temporal data mining for clustering and classification. It provides a very robust method of clustering, and normally it can be used to detect or to compare distance and similarity between different time series. Basically, DW has some very good property and which is useful for different applications. Normally, DW-based time series similarity measures is less sensitive to signal transformation. So if there is any time warping between these two time series, if there is any time shifting or any time scaling, DTW is able to match data points accordingly without any problem for time shifting or a problem. So in this case, DTW is less affected by time distortion and can be used very perfectly for pattern matching. So pattern matching is completely possible even in time distortion problem. This is the main benefit of DTW, and based on that feature of DTW, we use DTW for our implementation. Also, DTW has another feature. It can be implemented very easily. So its implementation is very easy, and because of these two features, two properties, we use DTW for our power profiling model. Okay, so let's very quickly review the DTW properties. Actually, DTW is a family of Euclidean distance family. If we want to measure this DCW distance or similarity between two time series like X and Y, each of them has N and M lengths. In this case, first we need to we need to find the best alignment between X and Y. In this case, first we need to calculate and set up an N by M matrix in which each item in this matrix is Euclidean distance between the corresponding items at each data series, xi, yj. In this, and the next step, we need to find a warping path like W, which is a data point, and each data point of this series, this item of this series is coordinates of corresponding data point in X and Y. So we can find different warping paths, but the best alignment or the best warping path should be selected, in which a warping path through the matrix with the minimum total cost. What is the minimum total cost? Actually, the minimum total cost is the minimum distance between corresponding data points in two sets, which is measured by this formula. So DTW actually is the warping path with minimum cost or minimum distance between the data points in these two data sets. Okay, we extract the definition of this DTW from these two references, which can be referred for more detail about DTW and their application. Okay, what is our proposed model for power profiling? Actually, our power profiling has 4 steps or 4 sections. In the first section or in the first stage, which is called data extraction, we extract electrical usage data measured in AMI system by smart meters. In the second stage, load data analysis, actually we try to extract consumption pattern from different usage or load data points by checking their similarity between different data points in DTW based on DTW algorithm. After that, we cluster different data points based on their similarity, and depends on in this case we focus on 2 items of time. So time of day and daytime. So it depends on being weekday or weekend or holiday. We try to have different classes and different cluster to have data classification. And after training and making our classification, we are able to assign our profile to each new measured data points or new measured consumption data points. Based on the similarity between this new measured data point with each of our profile, we are able to find if this data, if there is no information about the time, in this case, we are able to find if this data is a data measurement, power measurement measured in a workday or in a holiday or a weekend. And also, we can assign more clusters. For example, this data measured in the morning, afternoon, during the late night, and etc. Okay, let's I explain our model in more detail stage by stage. At the first stage, which is data extraction, in this case, we use real-world data set of electrical consumption from AMPDS2 dataset. This dataset is a publicly available dataset for data consumption, electrical consumption. This measurement is done for a long duration for 2 years and is done in Vancouver, Canada. And all data are extracted from different electrical devices like TV, like refrigerator, dishwasher, cooker, and by smart meters. In this measurement, then real-time smart meters devices were used, and especially for electrical measurement, Dent Power Scott 18, which is introduced in this address, were used. Data collection was done frequently per minute, and per day we have 1,440 measurement data points per day for each appliance, for each device like TV, refrigerator, and etc. So based on that measurement, we have a different data set of each device per day or per day. So we consider each data point of a day as a single power usage time series for our measurement. Okay. The next phase is extracting the feature or feature extraction of that data set. So for each case, we have our data measurement, and you can see that. Okay, so at each sorry. To extract the similarity or the features of data consumption, we implement DTW. We use DTW algorithm, and we implement DTW algorithm in Python by using DTW Python module, a library available online. We use this module and implement our code, implement DTW algorithm in Python, and measure different time series to measure and calculate their similarity, their DTW similarity. So this measurement is done point-to-point matching between each data points of different measurement or load data available in that website, that data set. Sorry. For our case, for this case. Okay, for this case, as I mentioned, in this data set, the power consumption of different devices are available. So we select refrigerator for our measurement and for our clustering because refrigerator has some properties. First, refrigerator uses power for all time. So for all point of time, refrigerator is working. There is no pause, there is no stop in refrigerator activity at each home. So because of, and also refrigerator shows a circular pattern of consumption, and based on that, we find refrigerator is a good device for our measurement. As I mentioned, this is a progressive work, and definitely to have more accurate of users' power consumption behavior, it is better to have more devices. But for this research, we only limit ourselves to refrigerator. So refrigerator shows different patterns, depends on users' behavior. And for example, in a workday and also in the weekend, the number of person at home is different. So the number of opening and closing the refrigerator door, or the number of time put stuff in the refrigerator or extract stuff from the refrigerator will be different. So because of that, you can see that there are different consumption pattern of refrigerator shown in different days. For example, in these two figures, you can see that the first one, the left figure, shows the daily or hourly consumption pattern of a refrigerator in a workday. You can see that for each day we make a separation between the usage pattern of the refrigerator. You can see that from first hour to the last hour, the consumption pattern, and compare this one with a holiday or with a weekend. So you can see that for the weekend, at some special time during the day, the amount of power consumption of refrigerator dramatically is different. Okay, so based on that, we select refrigerator for our measurement, and we extract the load data points of refrigerator consumption for our clustering, and also extracting consumption features. Okay. In this implementation, to extract refrigerator power consumption patterns, we analyze refrigerator power consumption for 3 months, and for this duration, we extract power consumption for each day and analyze their pattern check the similarity between different data point sets to find the similarity. The DTW similarity or distance between each day depends on the day type, being workday or weekend or holidays. Based on that, we introduce two profiles, workday load patterns. Sorry, we introduced two pattern set, workday load patterns and weekend or holiday load patterns. Based on these two load patterns, we measure their similarity, and based on their similarity based on DTW algorithm. Okay, clustering. So based on to this end, first to extract the features, we set a DW distance matrix, and based on that matrix, we introduce two profile load workday load profile exactly based on the workday load patterns, and weekend or holiday load profile or VLP exactly based on weekend or holiday load pattern. In this table, in table 1, you can see that our clustering, the output of clustering for each profile or each load pattern type is shown in this table. For example, here as I mentioned, we provide two load type patterns: workday load patterns and also weekend load patterns. For each of them, you can see that based on our similarity, we found that the workday load patterns averagely they have 1170 or 1170 DTW distance between data points, consumption data points in workday, and for weekend class or weekend profiles. In this case, the data points of the load data, they have averagely 1244.75 distance, DTW distance. So we find this similarity between the data points at each group or at each classes. Okay, so now we extract our features. We find the similarity between different data points and consumption data points sets, and now we are able to detect to classify any new consumption data points to find if these data points should be classified as a workday or as a weekend. So in this case, to find the load type of a new input data, so first we need to measure DTW similarity between the input load data time series and both predefined set for workday and also weekend. As I mentioned, for workday and for weekend in the previous table as I showed, we make a set of workday profile and a set of weekend profile, and each profile or each pattern set is a data point set of different measurement point which extracted from the class of workday or class of weekend. So when we have new measurement data, in this case, we measure the similarity between that data point set with each of them, workday and weekend. For example, in this case, you can see that we have a data measurement, power measurement data points of a day. So to evaluate our model, we remove the information data about the day or time. So we just have 144 data points of consumption data. So we don't know this day is a work day or a holiday or a weekend. So we measure this W distance or similarity between this data point set and each of our predefined profile, workday load pattern and weekend load pattern. For example, in this example, you can see that the distance between one day's data, 1 day's consumption data points and a workday load pattern is shown in this figure. As you can see that the distance between these two data sets is 1030. 1030. So in this, you can see that actually when this distance is located at this level, because the distance between the workday load pattern is less than 1170. So actually this day the new consumption load data should be classified as a workday because of our table. Okay, so to analyze and also to evaluate the accuracy of our clustering, we select the data measurement data point of 2 months, 61 days. Actually, this duration includes 44 work days and 17 weekend or holidays. We remove all information about data and time of each user data set and measure DW similarity between each day's power data consumption, power data sequence with workday profile, workday load pattern, and also weekend load pattern. So accordingly, depends on the distance and also refer to our table, we are able to cluster any new load data set and check the accuracy of our model. Okay, this table, as I mentioned, this table is a table of our clustering features or clustering patterns. So as I mentioned, we check the distance between the new power consumption data with each of them. If DTW distance between the new consumption data point set with workday load pattern is less than 1170, in this case, we can classify that one as a workday profile, or if the distance between that power consumption data points with weekend load pattern set is less than 1244. In this case, we can classify it as a weekend profile. So this table shows the result of our classification and also the accuracy. So you can see that we measured the different points of the classification, false true positive rate and false positive rate of our classification. So based on the measurement of DTW similarity with the workday load pattern set is shown in this column, and in the last column, the DTW similarity with weekend load pattern is shown over there. Our classification showed that using workday load pattern shows better performance because more than 90% rate for true positive rate we achieve by measuring DTW similarity to workday load pattern. And also by using the weekend load pattern, definitely we can have 75% of accuracy. So we find that using workday load pattern has better accuracy for our clustering. One reason of that one is that, as I mentioned, in our classification, in our training mode, we use the 3 months. 3 months of data, consumption data measurement, and during that duration, the number of work days was more than the number of weekends. So in this case, because of that, our training for workday has better performance and has better accuracy in comparison to weekend. And I guess this is a very clear reason for this gap between these two clustering based on workday or weekend for our clustering. So if we want to improve the clustering, definitely we need to improve the duration for our training to find more accurate DTW distance between consumption data series in same cluster, in same classes. To conclude my presentation, I would like to mention that in this work, which is a power profiling solution based on DTW clustering algorithm, we introduce this model in which this model is can tolerate time disorder, and if there is if there is any time problem or distortion between our data series, definitely our model can match the data points to measure the distance or to find the similarity between different time series to cluster based on our classification. So based on property of DTW algorithm, time disordered load data can be used to detect consumption pattern. So our model doesn't have any problem or limitation against time disordering or time warping. So we are able to extract power consumption features and cluster load type based on DW similarity. We introduced two load profile and two power load patterns. As I mentioned, we need to extend that one by adding more information about the time. For example, which time on day, morning, afternoon, night, and etc. And also because of the some special item of environment. So season has another factor. Warm season, cold season, definitely the feature or the pattern of usage will be different. So in this case, we need to add those classes to our future work. The evaluation showed that DCW clustering based on workday load pattern has better classification result, more than 90%. But as I mentioned, we need to enhance that rate by adding more data for our training and also adding more classes for clustering. Thank you for your attention, and if you have any question, please let me know, and it's my pleasure to present at this conference. Thank you, and have a nice day.